MIT, and he has since been at a postdoc at Berkeley, and you will be joining Stanford soon, correct, Adam?
Yeah, that's correct. I'll be joining Stanford Computer Science next fall.
Congratulations on that. And he is
Thanks.
going to tell us about pseudo-randomness and the AdS CFT correspondence.
Great. Yeah, thanks so much for the introduction, Scott. So this talk today will be based on joint work with Bill Fefferman at Chicago and Umesh Vazirani. So the subject of today's talk will be the AdS CFT correspondence of Maldacena, which many of you are familiar with. This is a conjectured duality between a theory of quantum gravity in anti-de Sitter space and a quantum mechanical CFT. And the conjecture is that these two theories are connected by a dictionary, which is a map from one theory to the other, which maps states in one theory to states in the other theory, and operators in one theory to operators in the other theory. So this dictionary is kind of the instantiation of this kind of homomorphism, or this sort of duality between these two theories. So you can see why this is a very exciting idea. The idea is that using this dictionary, you can construct the theory of quantum gravity by studying the dual quantum CFT. As a result, this has been a topic of major interest in the quantum gravity community, has already yielded many new insights into this area. So one of the central goals of this area is to try to understand properties of this dictionary map between the two theories. For example, what is the domain of the validity of this map? For example, which CFT states correspond to states that have smooth gravity descriptions in AdS? This might be some small subset of states, and what do those states look like? There are also a lot of work been done to explore kind of the entanglement and error correction properties of this dictionary map. But today, I'm going to be talking about some different aspects of this dictionary. And I'm going to be asking the question of kind of how useful will this dictionary be? And by here, useful, I mean in the sense of, if you have CFT states that maybe you haven't already analytically solved for what their gravity duals are, how much will this dictionary be able to tell you about the gravity duals of these theories? And how easy is it in general to apply this dictionary map from a computational perspective? This is very important because, for example, there have been some recent suggestions that perhaps using prototype quantum computers, we might be able to study quantum mechanical systems that are analogs of CFTs. And perhaps from this, we might learn things from quantum gravity. And if we wanted to push this program really far, it would be really convenient if this dictionary were really easy to compute or apply, because it would mean it would be, it would kind of open up a lot of possibilities for learning about the gravity side from studying these quantum mechanical systems. So the main results of our work is actually that this dictionary is a little more of a slippery object. So, and in fact, the main conclusion of our work, and what I'll be arguing for in today's talk, is that this AdS CFT dictionary has to be exponentially complex. That is to say, if I gave you an unknown CFT state, it even promised that it was, at early times with a smooth gravity dual and very nice properties. If I gave you an unknown CFT state, it would be really difficult to transform that state into its corresponding gravity state using a quantum computer. So this is what I mean when I state that the dictionary itself must be exponentially complex. There's one other possibility in our work, which is that our statement that we get in the end is either the dictionary is exponentially complex, or the quantum extended Church-Turing thesis is false in quantum gravity. So this is the possibility that the dynamics of quantum gravity might not be efficiently simulable by quantum computers. This would be very surprising if this were true, simply because most physical systems that we've studied, including, for example, work on quantum field theories, by Jordan Lee and Preskill and others, have shown that even quantum field theory quantities are efficiently simulable on quantum computers. So if that were true, this would be kind of the first example of a physical theory that we would have that that would not be simulable on a quantum computer, which would be somewhat surprising. So how do we reach this conclusion? Well, it turns out that the exponentially complex nature of the dictionary arises due to the presence of something called computationally pseudo-random states within some very specially structured and well-studied subset of CFT states, which arise in something called the wormhole growth paradox. And the existence of computational pseudo-randomness in this setting essentially means that the AdS CFT dictionary is forced to equate some quantity like complexity in the CFT with some quantity like volume in the AdS in the context of AdS wormholes. And I'll describe this paradox and this argument in more detail. But what is essentially happening here is that the dictionary is being forced to equate some quantity that's hard to compute with the quantity that's easy to compute. And this is what's forcing the dictionary to be exponentially hard. So since this dictionary is extremely hard to compute in general, one could worry that this might actually limit the utility of this AdS CFT dictionary in certain settings. And I'll provide some more kind of philosophical comments and discussions on kind of the interpretation of this result at the end of the talk. Okay, so in order to understand our argument, it's helpful to first refresh our memory as to what is this wormhole growth paradox. So this paradox was first identified by Susskind in 2014. And the paradox goes something like this. So we know that in gravitational systems, there are certain gravitational systems which do not equilibrate rapidly. So for example, if you take a two-sided AdS wormhole and you plot, say, the volume of the wormhole over time, this wormhole just kind of stretches out linearly. In classical GR, simply forever. In quantum gravity, we know that there should be some upper bound on this just due to the finite dimensional nature of Hilbert space. But what's happening here is that the wormhole volume of this gravitational theory is just something that just essentially never equilibrates or only equilibrates at very late times. On the other hand, the quantum mechanical theory of the CFT is a theory that's believed to be very rapidly scrambling, or a theory which very rapidly equilibrates. So it's more like a blender. So what do I mean more concretely by this? I mean, let's say you take some local observable O, and you plot its expectation value over time under evolution by the CFT Hamiltonian. Then its expectation value will saturate very quickly within polynomial time to its equilibrium value. So there's this mismatch of kind of equilibrium properties between these two theories. So what Susskind asked in 2014 is, what quantity in this right-hand side theory could possibly be the dual to wormhole volume? So by the arguments that I just gave, the dual quantity cannot be some simple local observable of the CFT. It has to be something kind of strangely non-local. But what could that quantity be? Okay, so in the same paper in which Susskind identified this paradox, he also proposed a solution to it as well. And his proposed solution was that the dual to the AdS volume is in fact the quantum circuit complexity of the CFT state. That is to say, the minimum number of quantum gates that one would need to prepare the state starting from some reference state. And this proposal has been called the complexity equals volume conjecture. There are other variants of this. The other proposed resolutions called complexity equals action, which have very similar flavor. Our arguments actually won't really distinguish between the subtle differences between these two. Okay, so why did Susskind propose this as a solution to it? Well, there actually is some intuition on why complexity might be a dual quantity in the CFT, that might have these desired properties that you want in terms of its equilibrium properties. So more formally, Suskind's intuition went something like this. So let's say we model our CFT state by some n qubit state, where n is the entropy of the black hole. Of course, a CFT is not actually qubits, but this is just a toy model. And let's suppose that there's some unitary u, which corresponds to time evolution by the CFT Hamiltonian for some fixed amount of time. I'll be fixing this to be a scrambling time in this talk for reasons I'll describe later. Well, then you can very easily, note that, the state of your CFT after t scrambling epochs is given by something like u to the t times your initial state psi, right? Where psi is the initial states, which corresponds to, say, a wormhole of 0 volume. That will happen to be, the state called the thermofield double state, but the details of this actually won't matter much for this argument. So Suskind's intuition was that the complexity of the state, e to the IHT times psi, relative to the state you started with, should roughly grow linearly with time. And the intuition here is that, well, as long as there aren't any shortcuts to preparing the state, then presumably, the fastest way to prepare u to the t times psi is just to apply u t times. So so long as there are no shortcuts here, then the complexity of these states should grow linearly with time. And if that were true, then that would give this dual quantity, this complexity quantity, exactly the correct behavior, and the same behavior that is true of the wormhole volume. All right, so Susskind, had this really nice proposal that complexity, is physical here. It's the dual to wormhole volume. So this is a very creative and thought-provoking proposal. So there have been a number of kind of subsequent works which have tried to kind of probe this conjecture and try to find supporting evidence for it to kind of see if this is actually a reasonable conjecture. And work has been done in this area both from the complexity side, for instance, works by Aronson, Brandau, Bodanowicz, and Balasubramanian et al. And these authors tried to show that, linear complexity growth for time-independent Hamiltonians or various models like the one I described is something that is plausible. It turns out actually proving something like this unconditionally would be extraordinarily difficult. It's probably beyond the reach of computational complexity theory, but they provide kind of necessary but not sufficient conditions for this to be true, which kind of bolsters this claim that it is plausible that the complexity could be growing linearly. There have also been a number of works from the gravity side, which have also tried to find supporting evidence for this conjecture as well. So in particular, works of Stanford and Susskind and Stanford and Shankar made the following argument. So they said, okay, let's not only consider time evolution by the CFT Hamiltonian, but let's also consider making some small perturbations to this time evolution. So in particular, let's say you start with your initial state, which is a thermofield double, and you apply this scrambling evolution u many times. But interspersed with this scrambling evolution, we apply some local operators, O1, O2, up to OL. And let's say that we apply a small number of these local thermal scale operators to the CFT. And they called these states shock states. And why is that? Well, it turns out that on the gravity side, these local operator insertions in the CFT look like shock waves that are throwing energy into the AdS wormhole and therefore perturbing its geometry. On the other hand, in the qubit-based model, in kind of the simple model we have for the CFT, these local operator insertions, we can think of them as kind of like the insertion of a 1-qubit gate into the evolution. So you're evolving by the normal Hamiltonian. You then say apply a local 1-qubit gate, then evolve again for some time, then apply another gate, and then continue. So the interesting and not at all obvious observation of these works is that they computed the changes to the wormhole's volume arising from these shocks and showed that at least the first order, the changes in volume induced by these high energy shocks actually correspond to the changes in the complexity of these states that you would expect from inserting local gates into the evolution of a scrambling of an operator that scrambles very efficiently. So this was kind of a really non-trivial bit of evidence in support of complexity equals volume, that this conjecture seems to have the right behavior for not only the thermal field double state under normal time evolution, but also for these shock states, which are these kind of small perturbations thereof. Okay, so this is a really interesting proposal that complexity is physical, just going back to our original picture. But when you show this proposal to computer scientists, it seems like a very interesting or provocative proposal. And the reason is that complexity theorists have known for a long time that computational complexity and circuit complexity is a very difficult quantity to pin down or understand. Most complexity theorists' initial reactions to this conjecture is, here be dragons. Like there's a lot of subtleties that might arise if you think that complexity actually is physically manifest in some way. So what is this discomfort that the complexity theorists feel? Well, the discomfort is that this complexity equals volume seems to be equating two different quantities, which are in some sense of very different types from one another. So in particular, computer scientists have known since at least the 90s that circuit complexity, at least in very general settings, is a quantity that's extremely difficult to feel or estimate. So in the classical setting, if I give you some function, it's really difficult to tell, and I give you some ability to apply that function. It's extremely difficult to tell if the function I gave you is very complex or if it's very simple. And there are actually analogies of this in the case of quantum states that I'll describe shortly, which also mean that in very general settings, the complexity of quantum states is something that's very difficult to feel or estimate. On the other hand, the wormhole volume sounds like it should be some quantity that's easy to feel or estimate, right? It kind of sounds like something that you should just jump into the wormhole and take out your tape measure and measure the length of the volume. It feels like a really physically easy or accessible quantity to measure. So it seems like there's some mismatch that this complexity equal volume conjecture or variance are equating to quantities which have very different properties. One is very hard to feel or estimate, the other one's easy to feel or estimate. But it turns out that formulating this discomfort rigorously is actually very challenging. The main reason is that this conjecture is really only talking about some very special subset of quantum states. These shock states, which are these small perturbations of some evolution of some local Hamiltonian. So maybe the complexity of this special subsets of states, maybe it's somehow easier to estimate or feel than the general case. These arguments that in general complexity is hard to feel or estimate rely on kind of sneaking in post-quantum cryptography or things like this into these constructions. They're very artificially engineered states. Maybe these states are so much simpler that they're easy to feel or estimate their complexity. Or it could also be that maybe complexity was just not the right dual to pick in the first place. Maybe the actual dual to volume is some other property of these states, and maybe that property is something that's easy to feel or estimate, even though complexity is not. On the other hand, it's also difficult to formulate this second statement that wormhole volume should be easy to estimate as well. And the reason is it turns out that no single observer in the black hole can actually estimate the volume themselves. It turns out that the amount of time that you have after you cross the event horizon of these two-sided wormholes is a constant, and you don't have enough time to get out your tape measure and see the whole interior, but before you die and get smashed into the singularity. So in this work, we sought to ask, okay, can this discomfort of the computer science theorist be realized in this setting? And if so, what would this mean for AdS CFT? So in this work, we actually ended up formalizing this computer science, this intuition, on both sides of this argument. So we had two main results. The first result was the realization that these shock states that arise in this wormhole growth paradox, that's to say, the exact same states that were the objects of previous study, are already something called computationally pseudo-random. And I'll get to a more formal definition of what this means shortly. But the kind of intuitive definition of that is that, if I gave you a CFT state which had some shocks applied to it, but I didn't tell you which shocks I had applied, then it would be extremely difficult to distinguish a state of this form from a hard random state. So in other words, the basic intuition for why this is true is that somehow, if you wait for many scrambling times in between the insertions of the shocks, well, this shock pattern just gets kind of diffused throughout your entire system. And it's very hard to reverse engineer what shocks you had kind of thrown in the first place. It turns out this also helps you obscure the length of time evolution of the state. And it also allows you to obscure whether or not we generated the state via this process at all. So immediately corollary that we'll end up obtaining from this computational pseudo-randomness property is that it's actually really difficult to tell these shock states apart. Even shock states which have very different lengths of time evolution, and therefore shock states which correspond to extremely difficult wormhole volumes. So this pseudo-randomness property is actually formalizing this sort of discomfort that complexity theorists feel with equating complexity with something physical. It's saying that the complexity of these states, or more generally, the length of time evolution that you've had of these states, is indeed some quantity that's something that's not feelable. That's to say, it's not accessible to simple or polynomial time experiments. Okay, so this is our formalization of kind of this first half of our argument. I'll discuss the second half of our argument and its implications for AdS CFT in a few slides. But I'm first going to take a brief tangent to describe to you, what is this computational pseudo-randomness property, and why do these shock states possess this computational pseudo-randomness property? Because this is actually really the core of our entire argument. All right, so the notion of quantum computational pseudo-randomness, while in the classical setting, computational pseudo-randomness has been formulated since the 80s. In the quantum setting, it was only defined rigorously very recently in work of G, Liu, and Song. And the definition, it's kind of a mouthful, but it goes something like this. You call some ensemble of efficiently preparable quantum states psi k a pseudo-random state ensemble if I picked a random one of these ensembles and gave you polynomially many copies of it, it would be really hard for you to distinguish that from the case where I gave you polynomially many copies of the same hard random state. So what do I mean when I say it's hard to distinguish them from a hard random state? I mean in the sense that no BQP algorithm, that is to say no polynomial time quantum algorithm, could distinguish them from hard random states. So yes, I see that Dan Harlow raised his hand. You feel free to ask a question. Yeah.
I'm somehow not understanding this because if you give me 2 copies of any pure state, I can do the swap test and immediately tell that it's not 2 copies of a maximally mixed state, and it doesn't matter which pure state it is.
Yes, so that's correct. But I'm going to give you polynomially many copies of this state, an arbitrary polynomial number of them.
Fine, but I'll just use
Yeah.
2. Isn't that good enough?
I mean, Daniel, the swap test will succeed with the Haar random states just as well as it will succeed with the pseudo-random states.
I
Right?
know, but so that therefore I can always distinguish them. Oh, I see. You're not trying to distinguish it from maximally mixed. You're trying to distinguish it from a Haar random pure state.
Right,
Yes,
right.
our random
I
pure
see.
state, I give you many copies of that.
I see. Okay.
So it's true, if you only had one copy, that would just be maximally mixed. But with many copies, it's not.
Okay.
It has the wrong
sorry,
way.
It's actually like a random symmetric state, right? It's maximally mixed,
Yeah.
but in the symmetric subset.
Yes, it's a random symmetric state, exactly.
And is this equivalent to saying this is a K design with a K that's bigger than any polynomial?
So it's not actually. So okay, so that's a great question. So yes, as Xiaoling's pointing out, it's kind of like a K design, but the difference here is that you have computational instead of information theoretic security. So okay, saying something is a Q of n design, if Q of n is our polynomial, that would imply that Q of n copies are information theoretically indistinguishable from that many copies of a Haar random state. But here, the security guarantee is weaker. It's saying, well, it might be information theoretically distinguishable, but maybe that information is somehow inaccessible to polynomial time experiments. So this is actually a fundamentally computational notion. There's not an information theoretic proof that these exist. The reason is actually, it has to do a little bit with the subtleties of the orders of operations of picking these polynomials. So with a fixed polynomial size circuit, it's actually not possible to create a T design which is secure for T is arbitrary polynomials, because basically if you had more copies of the state than you had of the size of your quantum circuit, actually it does become information theoretically distinguishable. I think this was pointed out at least in the Brandau, Harrow, Horodecki papers on showing random circuits are T designs, but it could go back further than that. But at least the argument appears in that paper. So it's not quite the same as a T design, but it's kind of similar. But it's really a computational notion instead of an information theoretic notion. Yeah, thanks. These are great questions. So in the same paper in which Ji, Liu, and Song proposed this definition of quantum pseudorandomness, they also showed that it is possible to construct ensembles that have this form, but they did so in something that looks like a very artificial setting compared to this AdS CFT setting. So they did it by using post-quantum cryptography and computing something like learning with errors in superposition to put phases on the random state, some very carefully engineered construction. And you could then show that, assuming this post-quantum cryptography is possible, that these states are computationally indistinguishable from random, even though they are actually information theoretically distinguishable if you give yourself enough copies. Okay, but in our setting, okay, so now the question we're going to try to show is we're going to try to show that these shock states are pseudo-random themselves. So in our setting, we have a much smaller subset of states at play, and we're going to try to show that this same pseudo-randomness concept actually appears here, even though we don't have access to implementing, say, forms of post-quantum cryptography. All right, so what's the intuition here? Okay, so the first thing that you want to note is, even though your evolution by scrambling time, U, is, scrambling in some sense, the states that you obtain just by applying U many times to the thermal field double, there's no sense in which these states are pseudo-random. So why is that? Well, we're assuming here that everyone knows the CFT Hamiltonian. So if you were given a state of this form, you could just time evolve it backwards and see if you ever end up at the thermal field double state. And using this trick, you could determine the length of time evolution of the state. And since you have a polynomial upper bound on this, you would know you only have to go back so far. So this would give you a way of efficiently distinguishing states of this form from random. So in some sense, the fact that Hamiltonian evolution is just as easy forwards and backwards means that just the normal time evolution of these states, does not create pseudo-randomness. Okay, so what's our idea here? Well, the idea here is to use these shocks that were allowed in the shock states as a secret key. So we're going to apply some shocks, but we're not going to reveal the pattern of the shocks. And the idea is that by inserting these local shocks, this will help us obscure the length of time evolution of the state and also help make these states look random to someone who doesn't know the pattern of shocks that we had applied. Okay, so that's a little hand wavy. Let me explain this in a little more detail. So the set of states that we're going to consider in our pseudo-random state ensemble are states that look like the following. We start with the reference state, the thermofield double state. We then apply the scrambling operator, and we then pick a random 1-qubit Pauli operator. It's called K1, which is either identity X, Y, or Z, and we'll apply it to the first qubit of the system. So this is corresponding to kind of a local operator insertion in the CFT picture. Okay, so we do that once. Let's say we then apply our scrambling operator again, then another random shock, then our scrambling operator again, then another random shock. So this defines some set. If you apply L total shocks, because there are 4 choices of each possible shock you could have applied, this describes some exponentially large tree of 4 to the L different shock states that you could have created by applying L different shocks to your initial state. So these shocks kind of create branching points in the evolution of this state. Now, if this unitary U, this scrambling evolution of the CFT were, say, modeled by a Haar random unitary, then one would expect that each state in this tree should be nearly orthogonal to every other state in the tree, right? This is just, you can do a simple Haar integral to show you something like, if you take a Haar random state and apply a Pauli X to the first qubit of that state, that renders it nearly orthogonal to itself with extraordinarily high probability. Like the inner product tends to be like 1 over the dimension. So what this means is that kind of all of the different states in this tree are distinct. So if I gave you an unknown state phi, and I asked you, well, was this state, one of the leaves of this tree, or was it a random state that had nothing to do with this tree at all? Then it should be extremely hard to tell if this is, to tell which is the case, essentially because this boils down to a very difficult search problem over this exponentially large space of possible states. And we actually prove the security of this scheme. We prove that this does reduce to some sort of search problem in a simplified black box model of this construction. That's kind of the main technical result of our work. And we then are conjecturing that this security would hold in the white box model, where U, instead of being like some sort of black box random scrambling evolution, if instead U is based is actually the evolution for a scrambling time. Now, it actually might be beyond the reach of complexity to prove the white box version of this theorem. It might be equivalent to proving post-quantum cryptography is possible, which is something that seems extraordinarily hard. But we provide at least this sort of evidence that at least in some simplified models, this state is plausibly pseudo-random.
Wait, Adam, by the black box model, you mean that the unitaries are Haar random, or what?
Yes, the unitaries are random, and all you can do is apply U or U inverse. So for fairness, you have to have like a symmetrical thing, because that's what's allowing you to reverse it. Actually, we sketch the proof in the quantum case. We actually prove it very rigorously in a classical analog that I'm going to describe shortly that captures all of the essential features of the quantum case.
That's it. So they're Haar random unitaries interweaved with shocks, which are like 1 qubit.
Yes. Yeah, and you can apply, so I give you the state, I tell you I made it in this way, I just don't tell you the shocks. you can apply, the statement is the number of times you would have to apply U and U inverse to distinguish this is like 4 to the L over 2 because it reduces to some, it just reduces to a search problem effectively. It ends up bottoming out on the Grover lower bound. And we're using the fact that the Grover lower bound works in the average case. Like this is an average case Grover lower bound, and hybrid argument lower bounds work in the average case.
Good, thank you. Now, there was a question in the chat, what is U prime? Is it U times X?
Oh, what is U
What is
prime?
prime in the diagram?
Did I define a U prime? Sorry, I'm.
You used it in the figure.
Oh, I used it in the figure. Yes, thanks. U prime means, yeah, say U times X, exactly. U times X on the first qubit. Or it should be a 4-ary tree instead of a binary tree where, there's U times X, U times Y, U times Z, but it's just easier to draw binary trees than 4-ary trees and still be able to read the diagram. So, yeah. Okay, thanks.
So can I ask a question?
Yeah, sure.
Yeah. So in this construction right now, you have because you want to construct this pseudorandomness state. So right now you have many possible choices of different kinds of shocks. So are you sure that this construction will not destroy the bulk geometry? That, for instance, it will change, for instance, the entanglement at the level of 1 over G Newton, such that this bulk geometry becomes a complicated ensemble or some superposition of quantum geometry, and then you're not able to deal with this problem.
Yeah. So this is a great question. So for this reason, we're only ever considering states where the number of operator insertions L is much less than the entropy of the black hole. Because I agree, there are concerns that, if you apply too many shocks, is there even a geometry to talk about on the AdS side? And the statement is going to be something like, however many shocks you think you can apply, like, let's say, you think you can apply, n to the epsilon shocks, where epsilon is some super tiny constant, so it's much smaller than the entry of the black hole. Then our hardness will be that our pseudo-randomness will be secure against time, like 2 to the number of shocks, basically. So it's almost saying that the larger the set of states for which you think complexity equals volume, or this whole picture is valid, the harder the harder it should be, the harder the dictionary should be. So if I haven't gone through the rest of the argument, but that's kind of, if you restrict your shocks to some super tiny amount, you're effectively then just restricting the domain of all of these arguments, but there still is an exponential hardness in kind of the size of the domain, basically.
So I'm just a little confused about the picture. So I think in holography, our experience is that there's a rough identification between the energy in the boundary, energy levels in the boundary, and the radius in the bulk. So, and it's just a simple linear identification up to some precision. So usually if we say that a thing is, a thing is local in energy, that means that a thing is local in the bulk geometry. So at least up to some precision. So so in your construction right now, say that you're in the energy level basis, and then you make this very complicated object, and in order to create your pseudo-randomness, I would expect that you also have a complicated bulk picture that you cannot deal with.
Well, so the reason we limited ourselves to these states are these are precisely the states that were studied by Stanford and Shankar and Stanford and Susskind. So these are the states for which they were able to do some sort of, at least some perturbative calculation of what happens to the wormhole volume. So I believe that for these states, at least for a small number of shocks, they should be well defined on the AdS side. In terms of your question about energy, that is a very interesting question. So what is true is that these operator insertions will, as you're pointing out, increase the energy of the CFT state. So a very naive implementation of the pseudo-randomness construction, like this toy model I just gave, you might worry that the energy of these states kinds of gives away the answer. Like, it might maybe you just need to measure the energy of the CFT state, and that might tell you how many shocks we applied. So what we actually need to use to argue that this white box security is plausible is we actually need to make a variant of this construction where we always apply the same number of shocks in every possible one of the pseudo-random states. So that way they have the same energy in the end. But again, we still don't reveal the pattern of shocks. All we reveal, we use that to hide different lengths of time evolution, basically. So yes, so there are some kind of subtle issues with energy that one might worry could break in the white box model that we don't have rigorous proofs for, but there is there are still a very large family of states of the same energy that one can obtain with different shock patterns that at least in black box models one would expect are extremely hard to distinguish from one another.
Yeah, I see. Thank you. So are you in the energy basis, or you are in the spin basis, just like the field basis in the CFT?
I'm assuming I believe I'm in the spin basis like this, but I'm not entirely sure that would matter very much for the argument. So if one is easier to look at than the other, then yeah. All we're using is that U is very scrambling in whatever basis you're looking at. That's really all we're using in the argument.
Adam,
Thank you.
Adam, in the black box model, it's not just that you'd expect them to be hard to distinguish, it's that you proved it, right?
Yes, exactly. In the black box model, it's provably hard. Exactly. The question here is whether, okay, now when U is replaced by evolution by CFT Hamiltonian, you have some additional abilities. One is you can measure the energy. There's not quite an analog of that in the black box model. So there's an interesting question as to whether there is a variant of the black box model where you could try to add a little more power that would be analogous to measuring the energy. It's not clear how to do that without destroying the black box nature of the model in the first place, though. So that's why we took kind of a more canonical quantum black box oracle model.
Okay, so you should move on because I'm watching the time.
Sure. Yeah, I'll move on. Okay, so I'll just quickly remark that this pseudo-randomness construction actually does have a precedent in classical complexity theory. Namely, it actually looks a lot like something called a classical block cipher. All right, so when people communicate securely over the internet, everyone knows that we use public key cryptography like RSA as part of the way that we communicate securely. But it turns out RSA is not very efficient in practice for communicating large amounts of information. So what people actually use after they exchange some secret key with RSA is they use something called a classical block cipher to exchange information. So what's the idea of a classical block cipher? Well, the basic idea is you fix some block size. So this is like n-bit strings. You fix an n, and you let sigma be a fixed but known permutation of n-bit strings that is highly scrambling. So sigma is something that's published, like everyone knows what sigma is. You can apply it forwards and backwards very efficiently. So what you do to use this sigma to encode information is you pick some secret key k, and you take your initial string x that you want to encode. You then scramble it with sigma, and you then flip some of the bits of your message with this secret key. So let's say you XOR your secret key into the block. You then scramble again. You then XOR the key in again. You then scramble, XOR the key, etc. You just repeat this many different times. And you then use this with the same key many different times in order to encode some very large amount of information that you want to exchange with someone else over a public channel. So why is this a reasonable encryption scheme? Well, the intuition is that this encryption scheme, if you know the secret key, is really easy to undo, right? All you need to do is take the encoded message you got, unscramble it by applying sigma inverse, then apply your key, then unscramble again, then apply your key, for this fixed number of rounds that were kind of set ahead of time by all the participants. But the intuition is that if you didn't know the secret key, it would be extraordinarily hard to get back your original message X, right? And the intuition here is actually arising from the scrambling nature of this permutation. So the idea is, okay, let's say I somehow managed to guess all the bits of my secret key correctly, but I was just off on one bit. Like I almost nailed the secret key, but I just messed up one of the bits. Well, the basic idea is if I tried to invert this procedure with this one incorrect bit, I wouldn't get anything close to the original message because of the scrambling nature of this permutation. Somehow, the fact I messed up one bit in the original in the key means every time I apply sigma inverse, that one bit of error kind of gets scrambled into errors of all of the different bits of the message. And repeating this many different times, you just end up with something that looks like complete garbage. So this is kind of the intuition for why block ciphers are secure. But what you can then see is that the CFT states that we're talking about, these shock states, are precisely a quantum block cipher. So the scrambling permutation is exactly analogous to our scrambling evolution by a CFT. And our secret keys applications are exactly analogous to these applications of these local shock operators. In our case, we happen to apply one shock at a time. That's kind of analogous to flipping one bit at a time, like not applying the whole key each time, but only one bit at every round. But those differences turn out to be negligible. This is basically directly a quantum block cipher. All right, so that's the summary of our pseudo-randomness construction. So now in my remaining 5 minutes or so, I'm going to describe to you, what the implications of this are for AdS CFT. All right, so let me just recall. So what I just argued is that the shock states that arise in the wormhole growth paradox are computationally pseudo-random because they look like a quantum version of a block cipher. So once again, this means that it's really difficult to tell these shock states apart with one another, even shock states which have very different lengths of evolution, that is to say, even shock states which correspond to very different wormhole volumes. So what this means as a corollary is that the complexity of these states, or more generally their length of time evolution, is not something that's feasible to BQP experiments. We expect that this should be exponentially difficult to estimate if all you were given were copies of the CFT state. And what this immediately implies is that whatever is the dual quantity to volume, be it complexity or something else, that dual quantity has to be something that's difficult to compute. So this is kind of a really interesting result because it's saying that this dual quantity has to be something like complexity. It has to be a quantity that's extremely difficult to compute. So actually, in a roundabout way, this ends up kind of justifying complexity equals volume or complexity equals action, because, well, at least those conjectures don't have any worse properties, as far as we know, than just picking complexity as the dual in the first place. On the other hand, we argue that the wormhole volume is indeed something that is easy to compute. And we do this by giving an efficient algorithm which achieves a very rough approximation of the wormhole volume. So what this algorithm looks like depends a little bit on your philosophy of what you think the AdS CFT dictionary tells you about the bulk. So if you believe that given a CFT dictionary, that given a CFT state after applying the dictionary, you just kind of can easily extract the global metric, then computing the volume of given an explicit description of a metric, is a relatively simple calculation. For the same reason that if you were simulating GR on your classical computer, it would be easy to estimate the volume. But on the other hand, one might want to take a little more conservative view here. Like, what if you believe in complementarity? So what if you think there's not even some well-defined global AdS state to talk about in the first place? Maybe it's only defined locally relative to the experiences of local observers. So even if you only believe that the dictionary allows you to reconstruct the experiences of local observers, we argue that nevertheless, volume is still a quantity which is computationally accessible. And the basic argument is that, well, if you had some kind of large but still polynomially bounded number of observers in the wormhole interior, who could either meet pairwise and exchange messages or not, before they crash into the singularity. Then by simply kind of counting the number of observers who managed to talk with one another, or also just trying to count the number of observers who were separated by horizons, this would give one some very coarse estimate of what the wormhole volume is. Now, and the idea is that somehow by classically post-processing the experiences of these observers, this would give one an approximation to the volume. Now, one might immediately object to this and say, well, okay, why is it reasonable to assume that you could post-process these outcomes? As I described earlier, these observers actually cannot talk to one another before they die, if they're actually living in the AdS state. So, in some sense, this kind of calculation of wormhole volume is not an experiment one could physically do. Well, the basic idea is that there's no need for this experiment to actually take place in the real world, because if you assume the quantum extended Church-Turing thesis, then you could have just simulated the experiences of these different observers, say on different quantum computers, and then combine the answers to post-process the results. So this is kind of like, you should think of this kind of like making a movie of what this experiment would look like, and doing something in the movie that's not physically possible, but is nevertheless efficiently simulable. We see this all the time in movies where using computers, you can simulate too good to be true feats of things that might violate the laws of Newtonian physics, but because they're still simulable, you could still make a movie of them and kind of determine the outcome of what would happen there. This is kind of what we're doing here. You just have to simulate the experiences of these observers separately, kind of make a movie of it, and afterwards, with a classical computer, you could piece together the volume, at least some very coarse approximation thereof, in a computationally efficient manner, even though that's not a physically possible experiment. So what does this mean? So why does this imply the dictionary is complex? Well, our first result said back in this wormhole growth paradox picture that whatever the dual is, it has to be something really hard to compute, like complexity. Our second result argued that the wormhole volume is easy to compute in some computational sense, again, not necessarily in a physical sense. Well, this means that the dictionary has to be equating a quantity that's hard to compute with a quantity that's easy to compute. Therefore, this immediately implies the dictionary itself has to be exponentially difficult to compute. This is because you can't have a polynomial time reduction from a hard problem to an easy problem. It's for essentially the same reason. So this means that in some sense, this dictionary might be something that's permanently under construction in some sense, or it might be a dictionary that is very difficult to compute for general states, or a very difficult physical transformation to apply. And one could worry that this could, in some scenarios, limit what we learned from AdS CFT. So I want to conclude with just a few philosophical comments on what this could mean here. I'd say there are kind of two different ways one might view this result. One way of viewing the statement that the dictionary is exponentially complex is you might worry that this is somehow a bug in AdS CFT. Maybe this is something that's undesirable because it might limit what one can learn about quantum gravity just from studying a CFT. You could worry this could limit it both in kind of what we could learn from experimental implementations of CFT dynamics, or kind of more generally what we might be able to learn about wormhole interiors from AdS CFT. So it's important to note that our arguments require reconstructing the interior, like the interiors of wormholes. So it could be that maybe this problem only arises in wormhole interiors, which maybe we thought might have been hard to reconstruct anyways, and might not apply to other areas of the AdS. In fact, Susskind has taken this kind of suggestion further and proposed that maybe this result is pointing towards a form of computational cosmic censorship. Maybe these violations of quantum extended Church-Turing thesis or high complexity dictionaries can arise in AdS CFT, but they always are shielded by horizons. So that's a very interesting suggestion. You know, this would be the analog of Penrose's cosmic censorship conjecture that singularities are always shielded by horizons. So that's one way of potentially viewing our results. Of course, one also might view this high complexity of the dictionary as a feature rather than a bug. So, for example, there was a recent paper by Kim, Preskill, and Tang, which was in a slightly different setting. It was thinking about one-sided black holes and AMP's paradox instead of two-sided black holes and AdS CFT. But they pointed out that there might be some ways in which computational pseudorandomness might create a form of computational protection of causality, which extends earlier results of Hayden and Harlow and Aronson and Susskind, where the basic idea is, you know, perhaps the high complexity of certain duality maps prevents people from, you know, modifying things in the theory non-locally. So, for instance, you know, they were thinking about the case of old Hawking radiation being dual to a black hole's interior, and maybe the fact that this duality is extremely complex might be preventing people, you know, living outside the black hole from performing non-local operations on the interior and destroying causality. So there could be some ways in which this dictionary's complexity is actually a feature of the theory. I think it's a really great question as to whether something like this appears in AdS CFT as well as in kind of the one-sided black hole case. Finally, there's the statement that in order to make our arguments, we had to assume the quantum extended Church-Turing thesis is true in quantum gravity. What if this is false? It's, you know, we kind of just use this as a kind of black box statement. But a natural question is, you know, what would a quantum extended Church-Turing thesis even look like in the gravitational theory? And, you know, it's extremely not obvious what this, how one would even define this. Like, how would you reason about computation in different reference frames? Exactly what information would you encode locally in the AdS? So I think that this is really pointing to a very interesting direction for future exploration. All right, and with that, I'm out of time, so I'll take any questions.
All right, thanks. All right, since we're running low on time, let's take some questions quickly. Chris Krylova?
Yes, so my question is, because your duality is coming mostly from like physical constraints that you're looking into to get your exponential complexity out. I was wondering just a pure computer science question. So have you considered from like neural networks, especially like the tree diagram that you showed, like feed forward propagation algorithms, things like that? So have you looked into that at all?
That's a good question. I don't know if there's a connection to neural networks, but there are definitely, ING, Leo, and Song already did give a kind of pure quantum computer science construction of pseudo-randomness from the existence of one-way functions secure against quantum computers. So I didn't describe their construction, but the basic idea is something like this. So say that you create a state which is an equal superposition of exponentially many basis states. And to each one of those states, suppose that you applied a pseudo-random phase in front of the state. So it's well known that classically, if you have a one-way function secure against quantum computers, this is equivalent to being able to create what are called classical pseudo-random number generators secure against quantum computers, or classical pseudo-random functions, which are functions that look random but are actually not, because they have low complexity circuits implementing them. And actually, it turns out that you can actually prove that those states are computationally pseudo-random, assuming your underlying one-way function is secure. So yeah, so I'd say there already is kind of a classical quantum computer science construction that exists for these. It just happens to be one that didn't work naturally in our setting. Okay, so you're looking at mostly then just pure quantum computing. You haven't really considered like other avenues yet. Yeah, I haven't considered any connections to machine learning algorithms or whether there's kind of pseudo-randomness arising naturally there. But yeah, that's an interesting question. Okay, thanks.
Okay, Shalian.
Hey, hi, Adam. I just want to understand a little more specifically, say in the black box model, when you have this tree, then what is the task? Is the task like what you prove to be very hard is distinguishing one of the any state with any other state, or is the statement about the whole ensemble?
So what you first prove is distinguishing a random leaf of the tree from a truly random state is very hard. And that immediately implies that distinguishing them from each other is hard, because you can just use the hard random state as like a hybrid intermediate. If it were easy to distinguish them from each, since they're both indistinguishable from random, they're also indistinguishable from one another. All of them look random, essentially.
So the statement is you take a random one random leaf of the tree, and then
Yes.
And I give you this
You get many copies.
I give you this same state for polynomial number of copies.
Exactly. That's hard from. I picked out a single hard random state. I gave you many copies of the same one.
But the U itself is already a hard random operator, or?
Yes, given access to U though. So you have the ability to apply U. So that's not where the exponential complexity is coming from. The exponential complexity is coming in not knowing which shock you applied.
Okay, thanks.
So it actually is information. You can actually show that these are information theoretically distinguishable. Why? Because these 4 to the L states, since L is much less than N, there are many fewer of these states than the dimension of the Hilbert space you're living in. So information theoretically, there is no security here at all. It's all coming from the computational statement that it's just very hard to reverse engineer your shock patterns, basically.
Okay, thanks.
So in the chat, Juan Carlos asks, why do we assume the evolution is random and chaotic? Where does that come from?
So I think this is coming to probably one of the quantum gravity theorists on the call can certainly chime in with a better answer than me. But I think it's just coming from some of these fundamental observations about black hole information paradox, that somehow black holes should be emitting thermal radiation and things like this. So even though it's a deterministic process, it should have extremely scrambling processes and make everything look thermal. But I'm sure someone can provide a more detailed answer than that if people are interested.
All right, Daniel.
Well, I just wanted to push back a little bit on your slide with the matrix. How do you?
Okay, sure.
I mean, among other, if you just want to say you just want to classically simulate the bulk, how do you know that you're solving the right equations? They're not obviously, they're not the CFT equations.
Yes. So this is where I have to assume the quantum extended Church-Turing thesis. So I'm assuming that whatever kind of AdS state the dictionary gives me, it's not entirely clear what that would be or what that would mean exactly, but that I could simulate the evolution of the AdS side. I could simulate quantum gravity efficiently with a quantum computer. So somehow I'm assuming that those dynamics of the wormhole interior are something that you could efficiently make a movie of. And if you break that assumption, then the argument breaks. So this is that possibility that quantum ECT is false.
Maybe another way of saying it is that I don't see that the length of the wormhole has any operational meaning once the wormhole is sufficiently long. At least not in the sense of something that I would expect to count as an observable, right? Like I could imagine, you have a chain of observers they're all in the wormhole, and they're sort of close enough that you can pass a message down the chain. Hey, did you get a message from the guy next to you? Okay, how about
exactly.
Tell the lady right. But you see, then in the end, whoever it is that decides the length of the wormhole, all they see is the person who came in, and so that person comes in and tells them a number. But they have no idea whether they should that's okay. There's a person there saying a number, but you don't know if that actually means anything or not.
Well, there's no need to trust this calculation, right? We're assuming you trust your own quantum computer to perform the simulation correctly and tabulate things up correctly. So I don't think there's an issue of trust. I think more what you're pointing out is that, this one person kind of couldn't see the whole chain, right? Like they couldn't see the whole picture.
Yeah, maybe.
But the point is, as long as you could just simulate each person's experience. So, each person says, yes, I was able to talk to the person left and right? As long as you could make the movie of what each person experiences, Well, at the end, it's a trivial classical post-processing. You just count up, how long the chain was of people who could talk to each other.
Well, except that we don't really think that all those people are independent, right? I mean, like, I don't know, this idea that you have the very long bridge is kind of, we don't, that's somehow that picture of what's going on in the bulk, we don't think is actually right? So that's the same picture that tells you that the Hawking radiation is mixed and so on. So, I mean, that picture is maybe okay
if you don't think
but
I think maybe you could put our result as taking complexity equal volume seriously. And we're saying, okay, if you actually take seriously that there is a wormhole with an interior which has a well-defined volume.
Yeah, I guess I don't, maybe is what I'm saying.
If you don't believe the wormhole interior exists, then yeah, I'm not sure if there's a variant of our argument that would work there. But what we're pointing out is, even if it existed in some sort of very non-local sense, where individual people can never experience really the volume, even if it just existed in some sort of distributed sense amongst all the observers, even that is enough to get a contradiction with, that says the complexity of the dictionary is high. So it doesn't have to exist for individual observers for the same reason that you could just make movies of what each person would observe and then collect their experiences in some non-physical way.
Right. So let's do Zhenbin, and let's have that be the last official question, and then we'll go into the break time. Okay. So Zhenbin.
Oh, thank you. For the pseudo-random states you are considering, it has a property that if I do a inverse time evolution, it will have a local particle excitation near the boundary, right? Yes. That's corresponding to, what that looks like completely different from just a hard random state. If I do a inverse U, I won't see any local excitation at the boundaries. So what? Yes. Yeah. So those are easy to distinguish.
So that's a really great question. So I think what you're pointing out is that our black box evidence for this conjecture, the pseudo-randomness statement, doesn't exactly line up with the evidence you would want for the white box setting, right? So in the black box setting, yes, we're showing these things are indistinguishable from random. And we're using as a corollary that they're indistinguishable from one another. But when you go to the white box setting, where you're actually talking about the CFT Hamiltonian, a hard random state might not even make sense to consider in this kind of framework. So I'd say that what we're actually conjecturing in this white box setting is that these different shock states are hard to distinguish from one another. I think that's the only part of our black box statement that still makes sense in this kind of white box setting where you're more taking into account the physics of the model. But yeah, I agree. You would actually expect that they would be distinguishable from random just because they would have different energies, right? These are, the shock states are low energy states, and a hard random state would presumably be a high energy state.
Well, so, well, you can make them have the same energy, but maybe it's a different flavor, which is also easy to distinguish.
Exactly. So that's the, when you start getting to the details of what makes sense in the white box construction, what makes sense is the same construction where, it's kind of like, as you're suggesting, each of the particle excitations that you apply to the boundary has the same energy, but is somehow of a different flavor. Like this is the equivalent of a Pauli X, Y, or Z that you're applying. And if you have the same number of excitations, all the states you're talking about have the same energy, but there can still be exponentially many of them, right? So that's kind of the variance of the construction you need to make it plausible in the white box setting. Yeah.
But then in the white box setting, could you just easily distinguish them from the flavor?
No, well, I think the point is that I'm not sure what measurement do you make on the quantum state to determine the flavor, like if you applied an X, Y, or Z? I'm not sure that that's something that's a measurable quantity. Like you can measure the energy. So if you have a low energy state and you apply an X, then it's true. If you have a local Hamiltonian, the Hamiltonian terms that were touched by that qubit that you flipped, will have a different energy. But if each of those energy perturbations has the same magnitude, I'm not sure if there's immediately a way to actually distinguish, those three possibilities from one another. So anyways, I think this is a great question. I think that there's a lot to ask about kind of the white box setting and what exactly one would need to do to make this reasonable.
All right, let's thank Adam again.